we are going to learn what is electricity. Electricity. When you hear the word electricity, you come across the electric lines in your street from which you draw electric current and use it in many appliances like television, bulb, electric fans, etc. Let us take an example. When you connect the phone charger to your phone, the phone automatically gets charged. Have you ever wondered why this happens? Let us look into what's going on there. In this chapter, we are going to learn electric current, potential difference, resistance, resistivity. Electric current. We are familiar with water current and air current. Similarly, the flow of charges constitutes electric current. Let us take the previous example. When the charges flow in the wire, we say there's electric current in the wire. Electric current is defined as the amount of charge flowing through a particular area in unit time. Or we can just say that rate of flow of charges is electric current. From the definition of electric current, we get I is equal to Q by T. 1 ampere is a really huge quantity. So to measure small currents, we use milliampere and microampere, where micro stands for 10 power minus 6 and milli stands for 10 power minus 3. The device used to measure current is ammeter, and ammeter is always connected in series with a circuit where the current has to be measured. A closed and a continuous path of electric current is called a circuit. To represent circuit, we use many symbols such as electric cell, electric battery, plug key open, plug key close, wire joint, wire cross, electric bulb, rheostat, resistor, voltmeter, ammeter, electric potential and potential difference. We know what is electric current. Now let us know why the electric current flows in the circuit. Let us take a perfectly horizontal tube and water placed in it. The water doesn't flow, but if we connect the tube to a higher level, the water flows from the higher level to the lower level. This is due to the pressure difference. Similarly, there has to be some criteria for the electrons to flow in the circuit, and this criteria is known as the electric potential difference. The work done to move a unit charge from one point to another point in a static electric field. The SI unit of potential difference is volt, represented by capital V. From the definition of potential difference, we get potential difference is equal to work done by charge. V is equal to W by Q. 1 volt is defined as 1 joule of work done to move a unit charge from one point to another point in a static electric field. 1 voltage is equal to 1 joule by 1 coulomb. The device used to measure voltage is voltmeter, and voltmeter is always connected in parallel to the circuit where the voltage has to be measured. The voltage in the circuit may be provided by the battery or the cell. The chemical action inside the battery and the cells provide potential difference across its terminals. Thus, we can see an energy conversion from chemical energy to electrical energy. Let us perform a small activity. Let us take a copper wire, 4 sets of batteries, each of 1 volt, a ammeter, a voltmeter, and a plug key. Let us connect the circuit as shown. Trial 1. Let us connect one battery and note down the readings of ammeter and voltmeter. Trial 2. Let us connect another battery and note down the readings of voltmeter and ammeter. Trial 3. Let us add one more battery and note down the readings of ammeter and voltmeter. Trial 4, let us add the last battery and note down the readings of ammeter and voltmeter. Now let us tabulate the readings and observe that V by I ratio remains constant in all the trials. The relation between V and I is given by Ohm's law. Ohm's law states that the potential difference across a conductor is directly proportional to the current flowing through it, provided temperature and other physical parameters remains constant. From the definition, we get V is directly proportional to I. To remove the proportionality sign, we introduce a constant. V is equal to IR, where R stands for the resistance. Resistance is the property of a substance to oppose or resist the flow of charges. The SI unit of resistance is ohm, represented by Greek letter omega. 1 ohm is defined as flow of 1 ampere of current in the circuit with a potential difference of 1 volt. Based on resistance, the substances are classified as conductors, resistors, poor conductors, insulators. Conductors offer a very less resistance. Resistors offer appreciable resistance. Poor conductors offer high resistance. Insulators does not allow the charges to flow through them, or we say they provide infinite resistance. Upon keen measurements and experiments, we see that the resistance is directly proportional to the length and resistance is inversely proportional to the area. To remove the proportionality sign, we introduce a constant. So we get R is equal to rho L by A, where rho stands for the resistivity. The SI unit of resistivity is ohm meter. Generally, conductors have a very low value of resistivity, and insulators have very high value of resistivity. Combination of resistors. To acquire certain amount of resistance in a circuit, the resistors are either in series combination or parallel combination. Series combination. When one end of this resistor is connected to start of another resistor, we say they are in series combination. Parallel combination. When two or more resistors are connected between the same 2 points, we say they are in parallel combination. Let us derive an expression for the equivalent resistance in series combination. For this, let us perform a small activity. Let us take 3 resistors, 4 voltmeters, 1 ammeter, and a battery, and connect these components as shown. We see that the voltage across the battery is equal to sum of the voltages across each resistor. So we get the equation V is equal to V1 plus V2 plus V3, where V1 stands for the voltage across R1, V2 stands for the voltage across R2, V3 stands for the voltage across R3. From Ohm's law, we know V is equal to IR. Similarly, V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3. By combining all these equations, we get IR is equal to IR1 plus IR2 plus IR3. Taking I common and cancelling, we get R is equal to R1 plus R2 plus R3. Equivalent resistance is equal to sum of individual resistances when connected in series combination. Hence, we can conclude when number of resistors are connected in series combination, the equivalent resistance is equal to sum of the individual resistances. Heating effect of electric current. Energy can neither be created nor destroyed. We can observe this when we use any appliance for a very long time. Let us derive an expression for the amount of heat dissipated in the circuit. We know power is equal to work done by time. From the definition of potential difference, we get work done is equal to V into Q. We also know that I is equal to Q by T. Hence, power is equal to V into Q by T. Power is equal to V into I. The energy is defined as power into time. So the amount of heat energy dissipated is equal to power into time. H is equal to P into T. H is equal to V into I into T. From Ohm's law, we know V is equal to IR. Substituting H is equal to I square R into T. Hence, we can say the amount of heat dissipated is directly proportional to the quantity of current and the time. Hence, we can conclude the amount of heat dissipated is directly proportional to the square of the current and the time during which the current flows in the circuit. The heating effect of electric current is also called as the Joule's heating effect. We can see many practical examples of Joule's heating effect. Practical examples of Joule's heating effect: electric iron, electric kettle, electric oven, electric heater. All these work on the principle of Joule's heating of electric current. Let us take the prime example, the electric bulb. A strong metal with high boiling point filament is used in the bulb. Most of the power consumed by the bulb is dissipated as heat and only some part of it as light. We can't feel the heat due to the thermal isolation provided by inert gases. Another example is the electric fuse. Electric fuse is made of thin metal and encapsulated in porcelain caps. When there is high current in the circuit, the thin metal wire heats up and melts and breaks the circuit. Hence, it is used to stop high currents in the circuit. It is also used to protect many appliances. Electric power. Electric power is defined as the rate at which energy is dissipated in the circuit. We know P is equal to V into I. P is equal to I square R. P is equal to V square by R. The SI unit of electric power is watt. 1 watt is defined as when 1 ampere of current flows in a circuit with the potential difference of 1 volt. 1 watt is a very small quantity. Hence, we use kilowatts to measure electric power. 1 kilowatt is equal to 1000 watts. The energy consumed in our household activities is measured by the term kilowatt hour. 1 kilowatt hour is equal to 1000 watts into 3600 seconds. We get 1 kilowatt hour is equal to 3.6 into 10 power 6 joule.